Thank you so much for having me. I am Mateusz. I work as a low-level security researcher at Google Project Zero. And today, as you already know, I will be talking about my latest research about the Windows registry. So let's get started. First of all, let's start with the fundamentals of the registry, what it is in the first place. So you may or may not know that registry is basically a database in Windows where most or all of the system and application settings are stored. So there are three essential concepts that you have to be aware of, which are hives, keys, and values. So hives are basically like standalone, smaller databases that are part of the registry, which are backed by files. Then inside of them, we have keys, which actually make the structure of the registry. And inside of them, we have 0, 1, or more values, which have the data that actually the applications want to save there. So Windows comes with some built-in tools for management of the registry. So you have registry editor, which is a GUI application. You have also reg.exe for command line modifications of the registry. You have very well documented registry API made available by Microsoft for developers who want to use the interface. And the most important part for us from the security perspective is that most of it is implemented in the kernel, which means that if we find any interesting bugs in the registry, we have a lot of potential for escalating privileges in the system. So in terms of the history, registry is super old. It's over 30 years old right now. It was introduced in Windows 3.1 to replace INI configuration files. Currently, a lot of the code and a lot of the design decisions of the registry, even in Windows 11, are directly rooted in Windows NT 3.1 and NT 4.0. So it has a lot of history. And at the beginning, it started very, very small as a very basic functionality. But over time, over the 30 years, it was extended and improved a lot. You may not see that a lot from the perspective of a normal user or even administrator, but internally, many things have happened, such as performance improvements, because registry is so central to the performance of Windows that it has to be fast. There were some backwards compatibility mechanisms introduced to make all the application works, and also some new features that are mostly relevant to software developers, such as supporting values bigger than 1 megabyte, supporting registry callbacks, which can be used by antivirus software, and so on and so forth. So this is a screenshot from the registry editor from Windows NT 4.0. And this is the registry editor from Windows 11. So as you can see, there isn't that much difference from the user perspective. On the left, we have the top-level keys and the key structure underneath it with some names. And on the right, we have the values associated, in this case, in the cursor's key. And the values have different types and different data stored inside of it. So that's basically how the registry looks like as a normal user. But the point that I wanted to make is, even though there is not that much difference in terms of the user interface, there is a lot of growth in terms of the code base. So what I did basically was I took every major version of Windows NT kernel, I decompiled it with IDA Pro and Hextrace, and I measured the number of lines of code that are responsible for handling the registry in every version and created this diagram. So you can see here that basically it started as a very small code base of around 10,000 lines of decompiled code in Windows NT 3.1, and it has grown increasingly over the years, basically tenfold, up to 100,000 lines of code in Windows 11 right now. So there is really a huge code base that we can attack as local attackers. So a little bit about my research. I basically spent a lot of time looking at the registry, basically between May 2022 and December 2023. So that's 20 months of research on the registry. And I found a lot of issues. So since I work at Project Zero, what we do is that when we find a bug and it has high severity impact, we report it under 90-day deadline and put it in the tracker. So I issued a total of 39 issues in the Project Zero bug tracker. There were also some bugs that had low or unclear security impact, which I reported outside of the tracker without the deadline. So far, I got a nice round number of 50 CVEs that have been assigned by Microsoft as a result of the research. And basically, because of how interesting and broad a subject the registry is, there has been a lot of, a variety of different attack targets, entry points, types of memory corruption, and many interesting bugs. So basically, if you are interested in general in the research, you can go to the Project Zero bug tracker. All of the bugs are now derestricted, so you can read all of the reports. You can download proof of concept files, and you can basically experiment with each of those vulnerabilities if you're interested to learn more. Similarly, I also made public the low severity reports on the Google Project Zero GitHub. And finally, I have started writing some blog posts about it on the Google Project Zero blog. And I will continue doing so because I have so many nodes of the registry that I want to share some information. So you can check that out. So far, there are 2 blog posts. But today, specifically, what I want to be talking about is logic bugs in the registry, which admittedly are much less common than memory corruption. So I think like 90% of the bugs I have found are memory corruption. But on the other hand, I think logic bugs really have that special something and are very interesting from a security perspective. Because when they are found, even they are not very frequent, they have interesting qualities. So first of all, they are very simple many times, and often when you find a good logic bug, you don't have to care about all of the different security mitigations that you have to bypass that you normally have to worry about if you're exploiting memory corruption. And if you know anything about logic bugs in operating systems, you know that symbolic links in particular often play a very big role, both in the finding and in the exploitation part of logic bugs. So it turns out that Registry also has symbolic links, which is very useful. They are very basic. Conceptually, they're basically the same as file system symbolic links. So what they do is that redirect access from one key to another key whose path we specify as the user or the attacker. Internally, it's just a simple flag that is being set in the key node descriptor inside of the Hive file. And also, we have to have a special value called symbolic link value with a special type of reg link that defines where you are redirecting the key to. And the whole symbolic following logic is implemented in the kernel. So in terms of creating symbolic links, this is a mechanism that exists, and some people know about it. It's kind of documented by Microsoft. It's only possible to do programmatically through the API. You cannot just open up Registry Editor and create a symbolic link, but it's still possible. It's available to normal users, so we don't have to have any special privileges in the system to create a symbolic link, other than it's been restricted in sandboxes since Windows 10, so that restricts the attack surface a little bit. So if you want to create a symbolic link, you just pass the special flag called reg option create link to the special API function that you normally use to create keys, and that's it. And you can see here in the Microsoft documentation that they don't really encourage people to use them. So it says registry symbolic links should only be used for application compatibility when absolutely necessary. So when you read something like this as a security researcher, you start smiling immediately because it means it's a good mechanism to abuse, probably. So here's an example again of the registry editor and how the symbolic link works. So here I have just created a symbolic link that redirects to the keyboard layout key. And if you open it in registry editor, you can see basically the same subkeys for both of those keys. So both sets of subkeys are the same subkeys, just visible through 2 different channels, the original key and the symbolic link that we have created. So that was a symbolic link created in the scope of single Hive. And the question is, what happens if we try to create a symbolic link between different Hives in the operating system? And if you think about it, this can potentially cause some security issues because you have many different Hives in the operating system and they have different roles because they correspond to different users. Some of them are system Hives. They have different trust levels and so on and so forth. So for example, if you imagine that you have a restricted user who creates a symbolic link in their own user Hive, and it links to a system Hive, and then you have a high privileged process such as winlogon who opens the key in HKCU and writes to it, then if such links are allowed, then you basically end up in a situation where winlogon writes to a location that the normal user wouldn't be allowed normally to write to, and you get some sort of privilege escalation. So the question is, what security domains are there really in the Windows registry, and which connections between Hives we have to really care about? So again, registry editor is super useful to analyze this. We only have to care about the HK local machine and HK users top-level keys here. So first of all, under HK local machine, we have global system Hives. All of these are basically defining system configuration, things that are global to all of the users. It also stores user passwords, policy information, and stuff like that. So these are very, very privileged and important hives. Then you have hives that are corresponding to users, but to the built-in user accounts such as system, which are also very privileged. Then you get the hives of normal users who have administrative rights. And finally, you have the normal hives, user hives of users which have restricted privileges. So you have 4 different tiers, with the first 3 basically being very privileged and being equivalent to being able to compromise the system fully. So all of these vectors are basically potential for privilege escalation if you can link from your own user hive of a privileged user to either the admin user hive, the system user hive, or any of the HK local machine hives. Something bad can happen. So obviously the question is, if you're doing this research, are cross-privileged links actually possible? And the answer is they were possible up to and including Windows XP. So, just going a little back in history, in 2009 and 10, Gynvael Coldwind and I did some security research. We did it mostly in Windows XP because I guess it was easier, and there was also still over 50% market share of Windows XP at the time. And we found a few bugs, including the CV 2010-0237, which was exactly the kind of confused deputy problem related to symbolic links, with the confused deputy basically being the winlogon process. So here is one slide from the presentation that we did at Confidence with Gynvael 14 years ago. And basically here we are the grandpa, and we are asking winlogon to read some values from some system hive that we normally wouldn't be able to read. So we got both the read primitive and also an arbitrary registry write, where we would be able to redirect a key to a system hive and have winlogon write there, and that would allow us to elevate our privileges. Just a little throwback to Confidence 2010. It was a big moment in my life because it was the first time I gave a presentation in English back then. And I'm actually curious, can I get a show of hands of who was at the presentation 14 years ago? Is there anyone? Can you raise your hand? I can't see. Okay. I hope to see you at my next registry presentation, Confidence 2038 in this case. So anyway, regarding Windows XP, so we found a bug, we reported it, and if you look at how it was fixed in Windows XP, you can see that basically a new function was added to the kernel, which decides if it's okay to follow a symbolic link from one hive to another. So the logic is very simple. Basically, we can have symbolic links within the scope of the same hive. And if it's a cross-hive link, that it's only allowed if the destination resides in HK users. So this means that they have killed this one attack vector of trying to create a link between our own user hive and a global system hive. However, the problem is that they still left these 2 other possibilities of attacking the hives of other privileged users in the system. And so it was an incomplete patch. The sad thing is that I guess we didn't verify it back then 14 years ago, so I only found out about the fact that it was incomplete like last week when I was analyzing it. It still continued to allow a few attacks from user to admin and from user to system. And it turns out the problem was never actually properly addressed, and it existed in Windows XP in some form until April 2014, when Windows XP reached its end of life. So the conclusion from this is, I guess, thoroughly verify fixes, both if you're a vendor, obviously, think hard about whether the fix that you're introducing actually fixes the whole issue, and also as a researcher, I guess, don't trust the vendor and always double check if you want to make sure that the bug was fixed. However, when it comes to Windows Vista and newer systems, they were never vulnerable to this kind of attack to begin with. Even Windows Server 2003 also was not vulnerable. And the problem was addressed internally at Microsoft at some point between Windows XP and Windows Vista. They refactored the symbolic link handling, and they introduced a concept called trust classes, which is basically a way to model exactly how these different hives, like the different roles and different trust levels of the hives in the operating system. And this requires some changes in the system call interface of the operating system. So the change that happened was basically that a new system call was introduced called anti-load key X, and that key had a new parameter called trust class key, which defines when you are loading a new hive, which group of hives or which specific hive this new hive should be in the same class trust class in. That basically solved the whole problem, right? Because now you were able to create groups of hives which could link between each other, but you wouldn't be able to have a situation in which you are linking from your own user hive to the user hive of any other user in the system or all the system hives. And the timeline of this vulnerability you can see here. So basically all of Windows NT were vulnerable, all of Windows 2000, Windows XP fully vulnerable until April 2010, and then partially vulnerable until 2014, and then the rest of the systems were not affected, thankfully. So that, I guess, that would in theory mean that the problem has been solved, because modern systems now do the right thing and they correctly isolate hives, so the deputies cannot get confused anymore, because it is just not physically possible for one process to open a key and then unknowingly operate on another key from another hive. This is just not allowed by the kernel. And that assumption holds true as long as there are no other types of symbolic links, right? That someone forgot about or something like that. So how do we make sure that there are no more mechanisms that work like a symbolic link in the Windows registry? Well, you can look at the specification of the Windows registry hive format. So the format is not officially documented by Microsoft. However, because of the significance of the hive format in forensics and security in general, many people have actually reverse engineered the format and created undocumented specifications. So a table from one of them can be seen here. And the table you can see is the list of different flags that you can set on a key that means something. So the assumption would be that if we go through the list of the flags that you can set on a key, you can basically figure out if there is any other way to create a symbolic link somehow. So I just started analyzing this table, going through the different flags, and we can do that now, going one by one. So basically, the first flag is key volatile. It is not used at all currently in Windows, so it's not relevant. Hive exit is just used for the mount points of the hives that you load in the system. It is kind of a symbolic link, but you cannot create it in any way as a user, so it's also not very relevant. Then the hive entry flag is set on the root of the hive, also not a symbolic link. Key cannot be deleted, also not relevant. Then we have the 0x10 flag, which is the symbolic link feature that we have just discussed before. So this is the flag that you normally have when you create a symbolic link, but that attack vector is now closed. Then we have something about compressed names of keys, also not super relevant. And finally, we have this flag 0x40, which is called key predefined handle, with the description is a predefined handle. So I was very confused when I saw that, because it doesn't tell me anything what this feature is about. So by comparison, symbolic links are also not very well documented in Windows, but at least there is something that we can start our analysis with, right? So Microsoft mentions it a little bit in the documentation. Other people have looked into it, blog about it, create some tools to create symbolic links and stuff like that. But for this kind of predefined keys, there was basically nothing when I Googled this. There are no mentions in any official documentation or anything like that, or even no references by any researchers. So this was very interesting and not very frequent you see something like that. Which of course is good and bad, because we have no sources to learn from, but at the same time, if there is a mechanism that no one knows about, we can be the first to reverse engineer it and maybe find something related, something interesting related to. So I will spare you the long process of actually reverse engineering the kernel to figure out what it does. I will just give you the overview. So this mechanism is also very old. It was introduced in Windows NT 3.1, so the second iteration of Windows NT. And it's not a real key. It cannot be used for most operations that you perform on a normal key in the registry. Instead, its core function is to redirect to a chosen top-level key, such as HKLM, HKCU, and stuff like that. The problem is that it cannot be created via any kind of API call. You cannot pass any special flag to create a predefined key. But if you control a Hive file in binary and you can just have the file loaded as a Hive, you can craft a predefined key in binary and have that accepted by the kernel. So here is an example of how it works exactly. So you have a small piece of C++ code, which is the standard type of code that you see when you want to open a key. So you just call the regopenKeyX function, specify the top-level key and the relative path, and what you get on the output is a numeric handle value, some small value like 11C that basically translates in the kernel to a reference to the normal key object, right? And you perform some operation on the handle and then close it. That's what happens normally. And with predefined keys, something weird happens. Instead of getting a direct small numeric handle value, you get a handle with the highest bit set, which basically is supposed to, it's like a pseudo handle to one of the top level keys, such as HK local machine. So that's the behavior. And you can probably see already where this is going. When it comes to what it's used for in Windows, I was wondering that for a long time. And I think basically there are just two keys in the registry which are predefined keys related to performance monitoring. So in Windows NT 3.1, you would open these two special keys to get performance monitoring information if you wanted to. And starting from Windows NT 3.1, instead of opening the special keys, you have to open the special HK performance text and NLS text top-level keys to get the same information. So I guess they just introduced it as a legacy mechanism to keep the old applications working if they were opening the registry key and not directly opening HK performance text. And as far as I know, this was basically the only legitimate use of those kind of predefined handles in the last 30 years. But there's a huge maintenance cost of that because you literally have two keys in the whole registry, which are predefined keys. But at the same time, they introduced a lot of complexity because when I was analyzing the code, I saw that it's important that no syscall operates on this kind of key because it has a different binary structure than the normal key in the Hive. So what's very important for security is that every system call in the system has to be specifically aware of this special type of key and reject it very early in the execution so that it's not operated on deeper in the kernel. Otherwise, you get different kinds of security problems like memory corruption and stuff like that. So, I wasn't really thinking about predefined keys as symbolic links to start with. I was just mostly focusing on whether there are any ways to smuggle in a predefined key to some system call where it normally shouldn't be handled. And I managed to find a few bugs, at least, where they actually would allow a predefined key to be operated on where it shouldn't. So there were at least 5 bugs related to that part. So they didn't get it completely right. But the bigger issue is, of course, that when you think about it, and it didn't come to me for a long time, but finally I realized that predefined keys are basically a type of another symbolic link. And they are not subject to the same trust classes mechanism that was introduced for mitigating symbolic links in 2010 and in Vista earlier. However, they are much more constrained than regular symbolic links that we used before, because first of all, we cannot create them through the API, only through the binary control of the Hive file, and also the destination is much more limited as well, because we cannot redirect it to any path that we choose in the registry. It has to be one of the top-level keys. So the question is, right, so we have this much more limited primitive, but it potentially crosses a security boundary. Can we reconstruct the exploit from 2010 or something similar with the primitives that we get right now? And this is what the presentation is about. So in order to be able to achieve any interesting results, we have basically 3 problems to solve. First of all, we have to find the Hive that we as a normal user have binary control over, that at the same time a privileged process operates on in some way. Then we have to find a specific operation performed by the privileged process that has some kind of security implications when it's applied to the wrong key. And finally, which is very connected to the second point, is that we have to find a top-level key that works well with the candidate from step 2. So it's all very much interconnected, and we have to find the right set of conditions to be able to exploit this. So let's focus on the problems one by one. First of all, finding the right hive. So you may or may not know that there's a special type of hives in Windows called application hives, which were introduced also in Windows Vista. And so any application without any special privileges can load their own hive with a call to reg load up key. And so that's a very good candidate when you start thinking about it, because we can control it in binary and we can load it on our own. But the problem is that application hives are supposed to be private to the loading process. It's not visible in the global registry tree, so there is not going to be a system service that will operate on them. And the other alternative is basically user hives again, which is the HK current user top level key. So user hives are backed by the entuser.dat file, which is placed in the home directory of the given user. There is a high chance that a system service will perform some kind of operations on HK current user, for example, when the user is signing in or signing out. But the problem is that user hive files are locked by the system when the user is logged in. So you cannot modify a user hive at the same time as that user is signed in. So if you go, for example, in Explorer to the home directory, you can see the entuser.dat files and several other related files. And when you try to open the file in any way through the API, or even if you try to open it in Notepad, what you will see is shown here. It will just give you a message that the file is locked and you cannot do anything with it at this point in time until you sign out as that user. Thankfully, there is a solution to the first problem, and it is a nice hack called mandatory user profiles. So basically, there's like a special logic in the user profile service, which is responsible for loading user hives, which, first of all, before looking for the entuser.dat file, it looks for another hive file called entuser.man. And if that file exists, it just loads it instead. And it has its uses in some scenarios. What's important for us is that it doesn't exist by default, and as a normal user, you can basically just create this entuser.man file, and you can have it used as the user hive. So the plan is basically to log in, copy a specially crafted file to the home directory as entuser.man, and then you log out, log back in, and the user profile service has now loaded the entuser.man file as your user hive. So you have binary control over your own user hive. So that problem is solved. The second problem is trying to find the right privilege operation. Here, there is a very neat tool called Process Monitor that can help us. So what we can do is, as another user in the system, we can start Process Monitor, set a very nice set of conditions that we want to monitor in terms of registry operations. For example, make sure that the user that is operating on the hive is anti-authority system, which means a system service, that the path begins with the path of our user hive, and then the operation is something interesting. So when you use Process Monitor, and then, for example, sign in, sign out as a normal user, you will get a list of all of the different operations performed on that specific hive by a system service. So this is quite easy. And of course, I did this experiment, and what I ended up with is this nice list of different operations performed by the services. In total, in my case, it was 456 events that I could analyze, and there were potential candidates for something interesting happening here. So in 2010, together with Gynvael, we used a primitive of winlogon writing to a special key called shell folders, which would initialize the different kind of paths for the environment, I think, such as my documents, my pictures, and so on and so forth. But that behavior is not existent anymore in Windows 11, so we have to find something else. But as you saw before, there are actually a lot of options to investigate. So I spent some time looking through the process monitor logs, and I found one interesting thing that I saw that the SVC host process was first trying to create a key called event system, HKCU software Microsoft event system, and then directly after setting some permissions on this key. So this could be an interesting candidate for the right primitive. And the security that the system service was setting was very permissive. It was basically making sure that the key would be readable and writable by the current user. So I did a little bit of analysis to figure out exactly what was happening. And my conclusion was that the process was corresponding to the system event notification service. The library that was doing the specific operation was the com plus event system, es.dll, and the functionality of that is basically this library would be called back every time a user logs in the system, and as I told you just before, it makes sure that the event system key exists in the user hive, and it also sets some permissive security on that key. So this is great for us in terms of exploitation, because if we manage to redirect this event system key to some top-level key, then we should be able to override the security descriptor of the destination key where we are redirecting. So that brings us to the third and final problem: where do we link to? For the complete list of top-level keys that exist, we can go to winreg.h header, and they have like definitions of all of the keys that exist. And you can see that there is quite a few of them, like around 10 or something. So it should be fine, right? There are many options to choose from. And you can pay attention to the title of the slides, how my face was changing when I was analyzing it. So let's start analyzing what could be useful or not. First of all, we have one top-level key that doesn't even exist in Windows 11 and any system after Windows 9X. So that's not usable. Then we have the special performance pseudo keys that are not really real keys, so we cannot set any security descriptor on them. Nothing interesting will happen, so also not very useful to us. Then we have the top-level keys related to the current user. And because of the fact that the process setting the security descriptor is a system, that means that it's the current user of system, which is kind of a privileged hive. However, I was not able to come up with any ways to use a write access to a user hive of the system user to get LPE. For example, the standard key that you use normally to get code execution as someone, for example, the HKCU software Microsoft Windows current version run, which is the autorun key, it's just not used by the system account. So I didn't have any good ideas of how I could abuse that specific one. Then we have the HK local machine and HK users top-level keys, which seem like good candidates, but upon further analysis, it turns out that they are not very good because of several reasons. First of all, they are not real keys. They are just mount points where other hives are loaded. And the most interesting subkeys of those two keys, for example, the software hive, the system hive, have protected DACL. So let me explain a little bit. Basically, what's happening in the code is that there is a call to set named security or something like that, a special API call to set the security of that key. And what is happening is that the security of that key is modified, and also the security of all subkeys inside of the tree that have inheritance enabled is also adjusted. But if a subkey underneath the key has protected DACL, meaning that inheritance is disabled, then the security of that key is not modified. So in this case, we wouldn't be able to modify any of the interesting subkeys of HK local machine, for example. So it's getting worse and worse. HK current config, this is another top-level key which basically redirects to some minor key within HKLM system, and it's just storing the current configuration, current hardware configuration, which doesn't seem like if we modify anything within it, we get any interesting primitives. And finally, we have HK classes root, which also looks primitive. However, there are a few problems with it. First of all, it's quite intrusive because of the fact that we changed the security of that key and also many of its subkeys. We are changing the security of quite a critical key in the system. So suddenly, some system services start misbehaving because they cannot get access to classes root. You get weird UI artifacts and stuff like that. So that's not very good. But also at the same time, all of the keys that I would normally think of modifying in HK classes root to get privilege escalation were DACL protected. So I also wouldn't be able to specifically modify the security of the keys that I would be interested in. And here you can see the legend. So I was hoping to use a little bit more of the green color, but really there are no good candidates based on this analysis so far. So I spent a good amount of time wondering what to do with this, because it seems like the bug should be very easy to exploit, and we just have to, go through the final hurdle to find the right primitive. And I finally had the idea of what we could do. So basically, the idea is that if you analyze the internals of the function that is being used to set the security descriptor, you see that it's following symbolic links, like the normal symbolic links instead of inside of the key, whose security is being modified. And at the same time, some of the top-level keys are standard keys in trusted hives. So for example, HK classes root is effectively HKLM software classes, and HK current config is some other key in HKLM system. And the nice thing is that if you have a symbolic link in a trusted hive, so a hive within HKLM system or software, you can have that symbolic link point anywhere in the registry. So what we can do is that we can trigger the bug for the first time to modify the security of the top-level key. Then we can set up a symbolic link somewhere inside of this top-level key to point it anywhere to any key that is not DACL protected, and we can trigger the bug a second time, and this time the set named security info function will follow the symbolic link and will also modify the security of the key that is pointed to by the symbolic link. So if we reevaluate a little bit the top-level keys based on this, we can see that two keys are actually quite well usable for the attack if we use the symbolic link technique. So basically, the summary of the attack that I would imagine is that you first get write access to HKCC, and I chose HK current config over HK classes root because it's a much smaller key, so we can just use it in a way that the system doesn't even notice that we have corrupted something. So first we get access to HKCC, then we set the symbolic link, we re-trigger the bug, and we get write access to some HKCR typelib GUID key that is basically configuring a specific COM object that is being used by the system process. And finally, we abuse the COM object to execute our own payload as system, and we register a debugger for the set HC or utilman. So basically, the third step is just to show that we have elevated our privileges, because we already get code execution as system, but of course, we want a nice command prompt to execute on our desktop running as system. So from the attacker's point of view, this is what is happening. So first of all, we are planting the specially crafted entuser.man hive file that redirects the event system key to HKCC. Then we log in and log out and log back in, create a symlink, trigger the vulnerability again. Then we have access to the special key in HKCR. We corrupt it. We log out again. And then, when we press, for example, Alt-U or spam the Shift key to use the sticky keys, then instead of utilman or set-HC, CMD.exe is executing, and we get full access to the operating system, and we get an elevated CMD running. So now it's time for a little live demo of the bug. So what we have here is a virtual machine running Windows 11. And we have a normal user that we log in as. And we have the exploit folder here. There's quite a few files that are required for the exploit. So the first step that we will do is we will take the entuser.man file, and we will go to the user directory and basically copy it there as entuser.man. Now we sign out. Sign back in. Font scaling got messed up a little bit. Let me fix that. Okay. Okay, so now we executed the first part of the attack. So what happened is that the bug was triggered, and we got write access to the HK current config. And we can see that in registry editor. So we have the top-level keys. We can go to HK current config, see the permissions, and we can see that for the current user, we have full control over the key. So that is great. So the next step we want to do is to create a symbolic link inside of that key. So that's what stage 1 is responsible for. Let me show you what it does. So that's it. We use a special program that I created called create symbolic link, and it's basically creating a symbolic link from HKCC to this HKCR path. So we will just execute it. And we are able to see the link here under HKCC, and it's pointing somewhere inside of classes root. So now we have to sign out again. Sign back in. The vulnerability is triggered a second time, so now we get write access to the key pointed to by the symbolic link. You can see that we also have full control over this. And now, time for the final stage. So we have this reg file, stage2.reg file. And let me show you what it does as well. So basically, it's just creating a new key and value under the key in HKCR that we are controlling, and it's just specifying a script that will execute as system whenever this COM object is activated. And then the script that we are executing, it's just a JavaScript shellcode that first of all removes itself from the registry so that it's not executed many times. And finally, it's adding a debugger to the sethc and utilman tools under image file execution options. So let me just apply this registry key, and then we sign out again. And finally, we press Windows U, and we get a shell command. And this shell is executing a system. And by the way, funny part is that Windows Defender comes into play here a little bit because it knows about this last technique of setting up a debugger for sethc or utilman or something like that. So it basically tries to remove the value as soon as I set it up or kill the processes when I press Alt-U. So what I had to do was basically start 3 command shells or something like that. And then the first one is killed by Windows Defender, and the 2 others are shown here, so they remain. So it's trying to do something, but failing a little bit. Anyway, it's game over anyway at this point. So when it comes to the timeline of this specific bug, you can see that it's much worse here because it has existed throughout the whole history of Windows NT pretty much up until July last year when it was fixed. It was also an interesting thing that Microsoft, first of all, when I was reporting some bugs related to predefined keys, they were only fixing the specific ways to exploit it and not deprecating predefined keys overall. But after 5 reports, they eventually decided, okay, predefined keys are not that important anymore, and we can really deprecate them and get rid of them completely. So that is very cool to see. And it would be nice if this was done in the first place, because it was really not a much needed feature, I think. So yeah, that's basically my presentation when it comes to takeaways, just a few things that I find cool. So first of all, the registry I think is very cool, as evidenced by how much time I spend on it. Of course, all the little documented / understood software features are very cool because it led to this very interesting discovery that, about something that no one else seems to have been aware of for the longest time. Also, logic bugs are very cool if you find a good bug. And finally, for me personally, presenting here after 14 years is super cool. So thank you very much for listening, and happy to answer questions.